All right, guys, let's begin. So we're continuing with our recap of the year. Today we're going over Chapter 4 and Chapter 5. So we're doing both integration ones together. They are both very short units. We sort of did both of them over 4 weeks, maybe 5 weeks. And the skills really follow on, so I think it makes a bit of sense to do them both together. So let's get straight into it. Again, I'll leave a summary of the integration rules for you there. The one that's missing is the integral of 1 on ax plus b, so we'll have to add that in there in a sec, so I haven't updated that part yet. Okay, let's move on then. Let's get straight into the questions. We've got evaluate, and we've got the integral of 6x squared plus 5x takes 7 with regards to x. So an indefinite integral, and we can evaluate it without simplifying. If you can see what it simplifies to, you can do that as well. The 6 is going to stay there. It goes to x to the 3 on top of 3. And then we'll have plus 5x squared on 2. Take 7x plus c. So just integrating in one step. Okay, what does it mean? It means if you differentiate this function, you will get this function. Now there's a lot of that happening in the exams. They're always looking for you to make a relationship, a link between the function and its derivative. So keep an eye out for that. Integral of e to the 4x plus 3 is going to be e to the kx plus ax plus b, 1 on a, e to the, so 1 on 4 in our circumstance, e to the ax plus b. And then the plus c hanging out in order for it to fill in for the constant. Okay, next we have 5x take 4 to the power of 3. So making sure we get all the notation right, our dx's when we need them and our plus c's when we need them. So this is ax plus b to the power of n. So it goes to 1 on a, ax plus b to the power of n plus 1 on top of n plus 1. So 1 on a, ax plus b to the power of n plus 1 on top of n plus 1 plus c. Okay, any questions? Stop me. Let's go for blue today. A, B, C, D. This one's going to follow on. We have 8 on top of the cubed root of 7x plus 2. And we're finding the integral of that. So the first thing we need to do is take that to the top of the fraction and express it as a power of a third. Okay, it's negative a third because we're taking it, we're putting it on the opposite side of the fraction, and it's the 8's just hanging out the front. It's a third because it's the cubed root. All right, and now we can see we've got the ax plus b to the power of n. That 8 that can sit there or it can come out the front. It's not going to matter. I'm just going to leave the 8 here, and then we have 1 on a, so 1 on 7, ax plus b to the power of n plus 1 on top of n plus 1. Okay, so when it says without simplifying, you can leave it like that enormous mess if you want to. You get full marks there. All right, if you want to do minus a third plus 1, you know, that's going to give you the 2/3, and it can simplify accordingly. All right, that's our question 1. Let's move on to question 2. So now we have a definite integral. We have an integral from 0 to pi on 2 of cos of x on 2. Okay, now this is something that pops up a bit as well, is this sort of x on 2. It pops up in calculus, pops up in integration, even in statistics for a probability density function. And what I want you to be aware of is whenever you see x on top of 2, always treat it as half of x. Okay, you can always pull that number out the front, and half is just a number, it's 0.5, right? You now have a coefficient of that, it's kx. All right, and the integral of cos kx is 1 on k sine of kx. So this is going to go to 1, so the half, 1 on k sine of kx from 0 to pi on 2. Okay, so this one's got the boundaries for the definite integral, so we're going to put those over here. We don't have plus c because it would cancel anyway. Now 1 divided by half is going to give us 2, so we've got 2 sine half of x. So I've got 2 sine half of x from 0 to pi on 2. So that's going to be 2 sine of half of pi on 4, pi on 2. Take 2 sine half of 0. And then we can go straight to our answer, but it's going to be 2 times sine of pi on 4. Sine of pi on 4 is root 2 on 2. So that part's going to simplify to root 2, and that part is 0. So the 4 steps you need for the fundamental theorem of calculus: you need the integral statement, okay? You need the integration with the boundaries, you need the boundary substituted, and then the answer, okay? Statement, integration, substitution, answer. 4 marks there using the fundamental theorem of calculus. Okay, let's move on. We've got find the area under the curve y equals x squared over the interval 0 to 2 using 2 rectangles. Find an upper estimate. Very good. Okay, so the function y equals x squared from 0 to 2, it's going to look like this. Here's 0, here's 2, we've got x is 1 here. The function is y equals x squared. So you can sketch that from your calculator. And we want to find an approximate estimate using 2 upper rectangles. So that's our first upper rectangle, and this will be our second upper rectangle. Alright, now each rectangle has a width of 1, doesn't it? And so you can, it doesn't really matter how you go about the statement, but you might just say the upper estimate or area upper is equal to 1 times the y value. Now the y value here, we base that off the x value. The x value is 1, the y value is going to be 1 squared. So the y value there is 1. And the y value here is going to be 2 squared, which is 4. So the first rectangle is 1 times 1, and the second rectangle is 1 times 4. So our upper estimate is 5 units squared. Okay, calculate the exact area using technology. So this is the thing we do need to know how to do, is using our calculator to evaluate definite integrals. So there's 2 ways to do this. All right, so make sure you know both. Okay, the first is just in run math. All right, so what we'll do is we go option calc integral, option calc integral, and there's an integral there. And you just type in the numbers, okay? And that's just going to spit out an answer for you straight away. It's not going to show you what the graph looks like or anything like that. So we've got x squared from 0 to 2. We've got 8 on 3. Okay, so that's part B. Part A is part B. Okay, that's the first way. The second way is maybe you've used the graph, and you can do it in the graph menu. So if we go into our graph and we graph the function x squared, we're graphing it from x is 0 to 1. We can, you know, even just setting it as a standard view window. All right, and one of the things we can do is G-solve across arrow. There's an integral button. Okay, so if we press G-solve, press the across arrow, and there's an integral button. That brings up lots of options. We just want to know the area under the curve, so we hit the first one. Make sure you're familiar with all of those, because it's a useful tool for checking your answers, right? And we want to know, we just type in the numbers. 0, 2, and we've got 2.6 recurring. Okay, so that's part B. Part C, will the lower estimate or the upper estimate be closer? So this is one thing I discussed a bit in wine glass folio feedback when we're talking about the prolate ellipsoid. This function is what we call concave up. It's opening upwards, okay? And because it's concave up, all right, if you think about the estimates, all right, I'll just draw some boxes here to illustrate it for you. The estimate, because it's curving upwards, let's exaggerate it a fair bit too, it's always going to be closer to the lower estimate. Okay, you can see there's more error occurring in this region than there is in this region, which means the lower estimate is closer if it opens upward, and you see the opposite effect if it's opening downwards. If we have a curve going downwards and we sketch a rectangle around it, okay, there, you can see there's more error in the underestimate. So our answer to part C is the lower estimate will be closer. Very good. So that's a summary of chapter 4, integration. And you might remember we did it sort of in a different order from the textbook. I'm not heaps happy with the order that the textbook does it in. So you can have a bit of a look at that. Let's move on to chapter 5. So it follows straight on. Now that we've got those skills, we're going to use them in a number of different ways. So the first one we've got 5a, area under the curve, so that's just graphical representation of it. Then we've got 5b, find the area between the function y equals x squared and the line, the horizontal line, y equals 9. So you can sketch both of these on your calculator and get the answer from there. Let's do both. What I might do, let's set up how we would perform this manually, and then we'll just get the answer using the calculator. So the function y equals x squared looks like this. The function y equals 9, okay, says y equals 9 for any value of x. It's a horizontal line, right? And we want to find the area between these two parts. So if we're using our calculator, what we'll do, we'll graph both of them and g-solve the area between the points of intersection. Okay? If we're going to do it manually, we could graph both and g-solve these points of intersection. All right? And then make the integral statement. Or we can determine the points of intersection. Graphs are going to intersect when they equal one another. They're going to meet when x squared is equal to 9. That's when they're going to meet. The first function equal to the second function. So that's going to be when x is plus or minus 3, right? So we have a negative 3 here, and we have positive 3 here. They're the x values. Now remember, when we're finding area between functions, it's the integral from a to b of the top function, the upper function, take away the lower function. Okay, so that means we're going to have the integral from minus 3 to 3, there where they intersect, of the top function, which is 9, take away the bottom function, which is x squared, all with regards to x. Okay, so now you can go through, you could process that manually using the fundamental theorem of calculus. You could type this statement into your calculator. You could graph them and do the g-solve intersection. Okay, there's a plethora of ways in which we could solve this. So, anyone solved it? So, 36. Thank you. So the area is 36 units squared. All right, move on. Let's go to 5c. We've got a kinematics question. Okay, so kinematics pops up in integration and calculus. They're not very common exam questions. You see them every now and then, but they're part of the course and they're a good application of it, so we're definitely going over it. Okay, all I'm saying, they pop up, they're just not very common. We have a velocity function, 1 take away 2t. Moves in a straight line. Find the total distance travelled in the first second of motion. Okay, so what's going on here is it's moving, we've got a velocity function. Now we want to find out how far it travels. The first thing we'll probably need to do is understand what does this velocity function look like. Let's graph it, or even just draw a sine diagram of it. Either's going to be fine. Remember, we only consider positive values of time, okay? And the root here is going to be positive half. isn't it? If you have 1, take away 2 times a half, the root is going to be 0.5. You can obtain that from the graph. You can obtain that by going 1 take 2t equals 0 and solving through. You get t is half. That's the root. The other thing to notice about this equation of a line is that it has a negative slope. So if it has a negative slope, it means it's going like this. And if it passes through that point, it means it's above and then below. Okay? So the graph of the line, like if you graph it, this is what it looks like. Okay? Now, we're asked to find the total distance travelled in the first second. So that means how much it moves to the right plus how much it moves to the left. Initially it's moving to the right because we have positive velocity, and then it's moving to the left because we have negative velocity. So there's a number of ways in which we can do this, but you could make a geometric argument, you could make an integral argument. Let's just go straight for the integral argument. We want to know the integral from 0 to 0.5 of the v of t function. Okay, that's going to tell us this area. And then we're going to add it to this area. All right, from 0.5 to 1 of the v of t function. But if we did that, our answer would be 0. And it's because these are symmetrical, and when you evaluate an area under the curve, it's going to come out as negative. Okay, so that means we need to account for that by, we want this quantity to be positive, so we can either just put the negative there, or we can put it out the front here. Remember, when you're finding area under the x-axis, it's 0, the function of the x-axis. 0, take away the function. So that's why I've got the negative v of t there. So we can evaluate that. That's going to give us the total distance, or 0.5 times 1 times 0.5 times 2. So let's just evaluate that. We've got 1 take 2x from 0 to 0.5. A quarter, and times 2, half. It moves half a unit, and we've got centimetres. Alright, so that's the total distance it travels in the first second of motion. Okay, find the displacement of the particle after 1 second. So let's go to the displacement function, and this is an opportunity for us to recap that. The displacement function is going to be t to take away t squared. Okay, when I integrate 1, I get t. When I integrate 2t, I'm going to get 2t squared on 2. Simplifies to t squared. Plus c, don't forget your plus c's. And that's where they pop up in kinematics, right? And so it wants us to find the displacement after 1 second. This function will tell you the displacement for any value of t. So we're finding s of 1. It's 1 take 1 plus c, c. Okay. We expect that to be the case, right? It's moving a quarter of a unit to the right, a quarter of a unit to the left. It hasn't changed its initial position. It remains the same. Okay, it still has a displacement of c units. Okay, move on. Question 5D. Okay, this is a good one. So we've got the rate of traffic flow past a pedestrian crossing between 8 and 8:30 is given by this equation in cars per minute, where t is the number of minutes after 8 a.m. Okay, now 2 things to point out. You're given the graph, okay, and whenever we give you a graph, even if we give you an empty Cartesian plane, it always has axes on it. And so that means we give you the constraints. So when you type in your V window, you've got your X min and X max, you've got your Y min and Y max. So use them, make your graph look the same. It's always provided for you. Okay, all right, find the rate of traffic flow at 8:20 a.m. Okay, so this is between 8 and 8:30. We've got the rate of traffic flow there. And so I'm just going to go straight off the graph rather than calculating it. I'll draw a very loose approximation of it so I can point where I'm talking about. looks something like this. We want to know when the time is 20, what's this? Because this is time since here's 8 a.m., here's 8:30 a.m. So we want to know when time is 20. All right, what's the rate? On the y-axis, we have the rate at which cars are passing through. And when time is 20, we can see very clearly it passes through 20. 20 cars per minute. That's our answer to part A. All right. Now the other way we could get this is if we've graphed a function and we're going to g-solve the y value. What's the y value when x is 20? Okay. Use the graph to estimate the time when the traffic flow is greatest. Okay, so I'm saying when is the rate highest? Right here, isn't it? And so that max point, 8:05 a.m. All right, answering in the context of the problem, don't just write t is 5. It's 5 minutes after 8:05 a.m. C, shade the region corresponding to t, the integral from t to from 10 to 15 of r of t. So if that's 5, here's 10, maybe here's 15, you're sort of shading this region. That happens a bit as well. And remember, area under a rate function is always a quantity. All right, so if we have a rate function and we shade an area under it, it's going to be the quantity. Now this rate here is the rate at which cars are passing through an intersection. So the quantity then is going to be the number of cars that pass through the intersection. Okay? It doesn't even ask us to calculate it, but the integral from 10 to 15 of r of t, that's going to be the number of cars that pass between the intersection from 8:10 a.m. to 8:15 a.m. That's part C. And then for part D, all we're doing is calculating the integral from 0 to 30 of r of t. Okay, because remember we want to know the total amount of cars that pass through. Well, that means it's the total area under the curve from 0 to 30, and we can just type that straight into our calculator and evaluate it. Anyone done so? All right, let's evaluate a couple of these things then. So I'll pull up an answer for both of these for you. So first, let's go from 0 to 30 of, we've got x to the 3 on 80. And then take x squared on 2 plus 4x plus 40 from 0 to 30. X to the 3 on 80, take x squared on 2 plus 4x plus 40. So I've got 1031.25 for this one. So to the nearest figure, 1,031 cars. And then from 10 to 15, $181.1, so 181 cars. Excellent. All right, so there's a pretty thorough recap of integration, chapter 4 and 5. So again, up to you how you're going to use your time today. Now, yesterday I emailed to you blank copies of the notes book, so it may be a good idea to pull out and have a go at some of the questions in there. Hopefully yours are floating around somewhere as well. And again, if you want anything printed, I'm very happy to do it for you. Let me know. But yeah, let's use our time today, hopefully doing some integration questions, and I'll put a few up from the 2018 exam that we can now have a go at. Let's get into it.